Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Welcome. You can imagine yourself resting beneath a wide and silent sky, the kind of sky that has been here long before any one of us opened our eyes for the first time. A deep velvet darkness gently pinned with distant starlight. Very old, very calm, very patient. And as you rest here, you are invited into a slow, unhurried line of thought. A question as ancient as storytelling, yet as modern as physics. What if reality loops? Not as fantasy nor as belief, but as a quiet scientific inquiry. A soft exploration of possibility. We are not here to persuade or to announce conclusions. We simply wander gently through ideas and see where they lead, while the mind grows quieter and the body sinks deeper into rest. Because the universe, for all its equations, for all its data, still surrounds us with mystery. And tonight we will sit with one of those mysteries as calmly as one watches the ocean tide rolling in and drifting out again and again. The thought is simple and yet immense. If space has no true edge and time stretches without end, then perhaps somewhere, somewhen moments repeat. Not symbolically, but literally. Not metaphor, but physics. A quiet possibility resting at the intersection of infinity probability and cosmic scale. To begin gently, let us look outward. For as long as humans have existed, we have tilted our heads toward the night sky and felt the quiet weight of immensity. In every direction we see galaxies spiral, arms of stars, clouds of dust and gas, clusters and filaments stretching farther than sight allows. The observable universe, the part we can in principle detect, is already unimaginably vast. Billions upon billions of galaxies, each containing billions upon billions of stars. And beyond that observable region, there may be more, possibly much more, perhaps an endless expanse with no boundary at all. In mathematics, when something is infinite, it does not simply mean very large. It means unending, limitless, inexhaustible. And infinity has strange consequences. In a finite space with finite ingredients, patterns repeat only occasionally, if ever. But in an infinite space with similar building blocks, repetition becomes not just possible, but statistically favored. This does not mean that every detail of your life must inevitably recur, but it suggests that if the cosmos is infinite, and if its physical laws are consistent, then the number of ways matter can arrange itself may be finite, even if the space it fills is infinite. And when finite arrangements are repeated over infinite distance or time, duplicates emerge. Just as if you had an infinite library of books printed with every possible arrangement of letters, you would eventually find not only familiar words, but entire stories repeated again and again, perhaps slightly altered, perhaps exact, simply because infinity leaves nowhere for uniqueness to hide. This is only a conceptual beginning, not a claim, only a gentle opening into what science means when it speaks of repetition. It is important to remain grounded in scientific humility. We do not say that this is how things truly are, only that current theories open the door to such possibilities. And so we hold the idea softly, like a fragile seed of thought resting in the palm of the mind. Let us return now to probability, because probability is the quiet language of large systems. When many particles or molecules or stars interact, patterns emerge, not because anyone designs them, but because mathematics guides the landscape of chance. We see probability in weather, in biological evolution, in the distribution of galaxies. Everywhere nature grows large, probability becomes the underlying rhythm, and in probability scale matters. When events have even the tiniest chance of occurring, given enough trials, they almost certainly will. This is not mystical or dramatic. It is the quiet strength of statistics. So if the universe is unbounded, and if matter and energy continue rearranging forever, then any configuration that is physically allowed may happen not once but endlessly. A planet like Earth forming in a star system like ours, a cell dividing and learning consciousness, a mind wandering beneath a night sky asking whether it has done this before. These thoughts are not predictions but reflections on what follows from scale. And yet there is an important distinction we must keep close. The difference between repetition in principle and repetition in reality. In principle, infinite systems favor repetition, but in reality we do not yet know whether the universe is infinite or closed or cyclic or something else entirely. We do not yet know whether time itself has a boundary, a beginning, or a repeating structure. And so while the mathematics invites repetition, the physical universe still guards its secrets carefully. Our exploration tonight is framed by that honesty. We are not declaring that you are living the same life over and over. We are simply allowing the mind to rest inside the possibility without urgency, without certainty. Because often the deepest calm is found not in answers, but in the willingness to sit quietly with questions. As you rest here, you might picture the slow rotation of galaxies, great spirals of stars turning over billions of years, patterns of motion steady, repeated, predictable, yet never perfectly identical, cosmic cycles stretching across time. Stars are born, they shine, they collapse their elements, seed new stars and new planets, and eventually new life. There is a rhythm to it, a natural recurrence. Even here on Earth, cycles shape our world. The rising and setting of the sun, the changing of seasons, the endlessly repeating circulation of oceans and air. We do not fear these cycles because they are familiar, reassuring, predictable. Eternal return as an idea sits at the edge between comfort and unease. On one side, it whispers of continuity of patterns that endure, of a universe that is stable, reliable, patient. On the other, it raises questions about meaning, about identity, about whether novelty truly exists or whether everything is only repetition in disguise. But tonight we approach gently. We do not dive into existential storms or philosophical intensity. We simply watch the idea as calmly as stargazers watch constellations drift overhead. The mind does not need to decide, only observe and soften. There is also a psychological stillness that comes from contemplating immensity. When we recognize how wide the cosmos is, our daily worries become lighter, more distant. Not because they do not matter, but because we see them in context. A life, one consciousness, one path through time, fragile, precious, temporary, set inside a universe so large that it exceeds imagination. And when we ask whether life repeats again and again, we are also asking about the nature of self, about the continuity of awareness, about whether there is something deep and structural that defines each of us. Science does not yet know, but it can quietly examine what might be required for repetition to occur. Infinity, large probability spaces, finite physical arrangements, consistent natural laws. These are not mystical ingredients, but measurable ideas studied in cosmology and theoretical physics. They do not prove recurrence, but they make discussion scientifically meaningful. And so, as you drift with these thoughts, your mind can relax, because nothing urgent is demanded of you. No conclusion, no belief, no defense, only curiosity floating like starlight over a calm and sleeping world. The night sky becomes a slow, patient companion. The galaxies turn, the universe expands, time flows, and through it all, you rest. The idea of eternal return is simply a lens through which to view that vastness. A way to ask, if there is no final edge to space and no terminal boundary to time, then what becomes of probability when it is allowed to run forever? Would every possible moment play out not once but endlessly? Would life repeat exactly down to the smallest thought? Or would only patterns echo while individual experiences remain singular, like one unrepeatable wave on a boundless sea? These questions stretch beyond certainty, and in that uncertainty there is room for stillness, because it reminds us that reality is larger than any single explanation or viewpoint, and that mystery can be peaceful. In the quiet of night, beneath the slow turning of stars, you are invited simply to rest with the thought that perhaps everything that is, everything that has been, and everything that will be exists within a fabric so vast that repetition is not strange but natural, not dramatic but statistical, not mystical but structural. and whether or not life truly loops. The contemplation itself opens a doorway into calm reflection. So breathe gently, allow the mind to soften and the body to settle. You are safe, you are small, and yet you are part of something immeasurably wide. And as you drift toward deeper rest, a final whisper remains. We begin a slow journey into whether everything we are and everything we do might happen again and again and again. Across thousands of years long before telescopes and space probes and modern equations, humans gazed at the sky and noticed something simple and quietly astonishing. Patterns return. The sun rises and sets, then rises again. The moon swells to fullness, then fades, then swells once more. Seasons rotate fields empty, then bloom, then rest, and then bloom again. Birth, growth, decline, and death, followed by birth again. When early societies looked at this rhythm, they saw not randomness but order. A structure to time, a sense that beneath the flowing world something constant persisted. And so long before physics, the idea of eternal return was born. Not as speculation, but as quiet observation folded into culture, myth, and philosophy. Let us walk gently through some of those ancient visions, not to endorse them, but to understand how humans have always searched for meaning in cosmic repetition. In the traditions of India, time is not a straight road. It is a circle. A great cosmic wheel turning slowly through unimaginably vast spans known as kalpas. Entire universes are said to arise, flourish, and dissolve over and over across cycles, so long that human history is but a faint whisper within them. Creation, preservation, transformation, not once but endlessly. Here repetition is not despair nor punishment. It is simply the way reality breathes, a cosmic rhythm echoing through eternity. In the philosophy of the Stoics in ancient Greece, another notion of recurrence emerged. They imagined the cosmos as a rational, interconnected whole, governed by natural law and destined to pass through repeating cycles, sometimes expanding, sometimes contracting, sometimes dissolving in fire, only to be born again. Not chaos, but order. Events may return because the underlying structure of the universe is stable, predictable, and self-renewing. Here, eternal return is a byproduct of rational nature, a universe so consistent that history itself may rewind and replay. Across the world, among the Maya, time was also layered and cyclical. Their calendars did not merely count days, they wove patterns of sacred significance. A day returned, a season returned, a cycle of ages returned, not as an exact copy but as rhythm. Time was not a straight path marching forward from beginning to end. It was a living pattern, repeating, renewing, breathing, and humans were part of that pattern, woven into it like threads in a tapestry. In these ancient visions we see a common truth. People did not imagine time as a line. They felt it as a circle, a returning river flowing endlessly past familiar shores. And as civilizations rose and fell, this intuition persisted. Empires bloom, expand, fracture, fade. New cultures rise, build, dream, and decline. The pattern repeats. History from a distance resembles the slow beating of a cosmic heart. This rhythm comforted some and unsettled others. Because repetition has two faces. One side is soothing. If patterns repeat, then life is part of something stable, predictable, rooted in the deep structure of existence. There is safety in cycles. We know that spring returns after winter, that dawn follows night, and so eternal return can whisper reassurance. Nothing is ever truly lost. The other face is darker. If everything repeats exactly without variation, then perhaps nothing is new. No choice is truly free. No event is singular, and life might begin to feel like a performance rehearsed again and again without end. This tension between comfort and unease has followed the idea of eternal return through history. It rises again in the philosophy of Friedrich Nietzsche. He asked a stark and unsettling question. What if every moment of your life has already happened and will happen again in the same order, the same sequence, the same feelings, the same outcomes, forever? He did not present this as a scientific theory, but as a psychological mirror. If life were to repeat infinitely, would you embrace it or despair? Would meaning deepen or dissolve? In Nietzsche's thought, eternal recurrence became a test of the soul. Could one affirm life so fully that one would welcome its exact return again and again without alteration, not even to remove its sorrows? This was not about cosmology or physics, but about the human capacity to say yes to existence. exactly as it is. The idea draws us inward into the depths of identity, value, and choice. And yet, beneath the philosophical layer, we see the ancient intuition again, that perhaps time is not merely flowing forward into novelty. Perhaps it curves. Perhaps it turns back on itself like a great cosmic loop closing without end. Across cultures, this intuition emerges naturally, because humans observe cycles everywhere: day and night, season and harvest, birth and death. Civilizations rise, learn, forget, and fall. Then others rise, bearing echoes of what came before. We sense a patterned universe, and we wonder, if small patterns repeat, might large ones repeat also? Might entire histories recur like seasons on a cosmic scale? But there is an important distinction that ancient thinkers rarely made explicit: the difference between symbolic cycles and literal repetition. Symbolic cycles describe repetition of form, not of detail. Winter returns, but not the same winter. New snow falls on new ground under new skies. The pattern repeats, but the instance does not. Literal recurrence is far stronger. It suggests that every single detail, every molecule, every thought, every event returns identically, as though the universe were a film played over and over and over. This stronger version rarely appeared fully developed in early myth. Instead, they embraced rhythm, not strict duplication. The idea that literal repetition might arise from the laws of physics is a far more recent development. Yet the seeds were planted long ago. Because once the mind recognizes cycles, it becomes natural to ask, how deep do they go? To the seasons, to the stars, to the structure of the universe itself. And as philosophy matured, so did the questions. Thinkers began to explore the human emotional response to recurrence. Why does repetition sometimes comfort us and sometimes frighten us? Part of the answer lies in meaning. When events repeat symbolically, we see order. We find narrative purpose, structure. Life feels woven into something larger. But when we imagine perfect duplication replaying endlessly, we sense a loss of agency. If everything is predetermined down to the smallest thought, then perhaps freedom dissolves. And yet the opposite realization can also arise. That repetition does not erase meaning. It may simply reveal that meaning belongs not only to novelty but to experience itself. To live, to feel, to think, to love, to question may carry value even if in some vast structure those moments echo across time. The human response to eternal return has always balanced between awe and dread, between serenity and disturbance. And it is precisely this delicate tension that has kept the idea alive through thousands of years. As long as people have watched the turning sky, they have sensed that time may not be linear, that existence may move not forward like an arrow, but around like a wheel. In this gentle exploration, we notice something important. Eternal return is not a new thought emerging suddenly from modern science. It is one of the oldest questions the mind has asked, a response to the quiet realization that the universe is rhythmic, and that rhythm may extend far beyond the boundaries of our brief lives. When you look at the stars and feel a sense of calm or wonder or distance, you are standing in the long lineage of humans who have done the same, seeking meaning in the turning patterns of the cosmos. And deep within that search rests the simple, enduring question: does reality repeat, or is each moment utterly unique, passing once and never again? The ancient dream of eternal return is our first recorded attempt to answer that question, not yet with equations or telescopes, but with stories, rituals, and philosophy. It shows us that the idea did not begin with abstraction. It began with human eyes looking upward, noticing cycles and quietly imagining that perhaps the universe itself moves in circles, a thought so soft that it can accompany you as you drift toward rest, a thought as old as starlight and as persistent as the turning of the night sky. When early humans watched the sky, they were not only looking outward, they were quietly looking inward as well. The patterns they saw above mirrored patterns they felt within, waking and sleeping, breath in and breath out, moments of joy and moments of loss. Life seemed to move in curves, not straight lines. In the traditions of India, this intuition was raised to a cosmic scale. Hindu cosmology imagines time as a hierarchy of cycles, days and nights of gods, ages called yugas, and even larger spans known as kalpas. A kalpa is not simply a long time. It is a full lifetime of a universe. A universe can be born, evolve, decay, and dissolve, and then another arises, within an underlying reality that does not end. Creation, preservation, and transformation are not singular events. They are recurrent processes woven into the structure of existence. In this vision, the cosmos itself has seasons. Universes bloom like flowers in a garden of inconceivable scale, then fall only to make room for new blossoms. Nothing is permanent, yet nothing is truly lost. Forms dissolve, but the underlying process continues. Here, eternal return is gentle. It is not about the exact replay of your individual life. It is about cycles of manifestation and withdrawal, about rhythms deep enough to cradle entire universes. In the Stoic philosophy arising in the ancient Mediterranean world, we find another articulation of cosmic cycles. The Stoics regarded the universe as a single living organism, filled with reason ordered by law, permeated by a guiding principle. They envisioned vast cycles in which the cosmos periodically passes through a phase of destruction, often imagined as fire, and then is reborn from that very state. The same natural laws, the same structure, the same order, possibly even the same events. The idea is subtle. If the universe is governed by unchanging rational laws, and if those laws act on the same starting conditions, then the unfolding may be the same each time. The Stoics debated how literal this recurrence might be, but the core sense remained. The world is not heading toward a final end. It is moving through cycles of transformation. Again, we see the intuition that reality may be fundamentally repetitive, even if our perspective is too narrow to see the full loop. Across the ocean among the Maya, time was measured with extraordinary care. Their calendars intertwined short cycles and long cycles, daily rhythms, ritual cycles, and multi-century patterns woven together. Time was not only quantity, but quality. Each date carried a characteristic flavor, a pattern of influence. As cycles completed, they did not simply end, they reset. A great sequence of days would finish and begin again, not as a copy, but as a continuation. This cyclical vision gave structure to myth, ritual, and social life. Important events were understood against a background of repeating patterns. Creation itself was not a single event, but part of a recurring process. In all these traditions, one theme is clear. Eternal return begins as a way of making sense of observable cycles. The sun returns, the seasons return, life returns. It becomes natural to imagine that larger structures also return, that the universe itself moves in rhythms too vast for any one person to witness in full. Later philosophy takes this basic insight and turns it inward onto human experience. This is where Nietzsche's thought enters the story. He invites us to perform a mental experiment. Imagine that one night you are visited by a simple statement, that every detail of your life, every joy, every pain, every small decision, and every great turning point will recur again and again in exactly the same order, not once but infinitely many times. There will be no variation, no alteration, no improvement, no editing, the same friends, the same strangers, the same meetings, the same losses. The same thoughts you are having now, played out on an endless cosmic loop. How does that idea feel? For some, the thought is crushing. If everything repeats in exactly the same way, then there is no escape from mistakes, no revision, no true novelty. The weight of existence grows heavier. For others, the idea becomes strangely affirming. If some pattern of reality affirms this life again and again, then perhaps your existence is not trivial. Perhaps it is valued by the structure of reality itself, the same life chosen again and again by the underlying pattern. Nietzsche's question is not about physics. It is about you, about the stance you take toward your own existence. If you knew that this life would return eternally, would you resent it or embrace it? Would you wish to rewrite its moments, or would you affirm them so deeply that you would welcome their return? In this way, eternal recurrence becomes a psychological tool. It magnifies our relationship to each decision. If each act were not a one-time occurrence, but part of an infinite repetition, how would that change your sense of responsibility or meaning? Again, this is not about whether the cosmos actually works this way. It is about what happens when the mind contemplates its own life under the lens of recurrence. Behind this thought experiment lies a broader observation. Humans are drawn to cycles. Our biological rhythms follow daily and yearly patterns. Our memories move in loops. We revisit old events in thought, reliving them with slightly new emphasis. We tell stories that circle around familiar themes: love and loss, hope and fear, courage and regret. Our cultures rise and fall. Technologies appear, transform the world, and then themselves become obsolete. New generations struggle with issues that echo older struggles. Even when the details change, the underlying patterns feel familiar. This repetition shapes our sense of history. We speak of cycles of boom and bust, of eras of stability and disruption. We notice that certain structures of power and conflict seem to return, perhaps altered in language or scale, but recognizable. This can be comforting, because it suggests that instability, uncertainty, and challenge are not signs that something has gone uniquely wrong. They are part of the ongoing rhythm of collective life. It can also be unsettling, because it raises the possibility that progress may be less linear than we like to imagine. That we may be orbiting around similar themes, rather than moving cleanly away from them. When we think about eternal return, we are really thinking about the depth of these cycles. Do they capture only patterns or also particulars? This brings us to the crucial difference between symbolic cycles and literal recurrence. Symbolic cycles operate at the level of structure. They say that certain shapes of event return, but not the exact same instance. For example, a society may experience a period of rapid growth followed by strain and fragmentation. Centuries later, another society goes through something similar. The situations differ, the people differ, but the pattern echoes. In personal life, one might enter relationships with similar dynamics, not because the people are the same, but because one's internal patterns draw similar experiences. These are cycles in a structural sense. They describe how forms repeat without claiming the literal duplication of moments. Literal recurrence goes further. It suggests that every particle, every configuration, every event returns identically. Not just another war or another love story, but the same war, the same conversation, the same thought you are having right now. Many ancient traditions did not explicitly spell out this stronger claim. They were content with structural cycles. Ages of the world turning and returning, universes being born and dissolving, lives appearing and disappearing, without insisting on numerical identity between cycles. But even if not stated, the intuition sometimes hovered nearby. For if the same conditions reappear and the same laws operate, it is natural to wonder how similar the outcomes become. The step from structural cycles to literal recurrence is subtle. And it is here that modern science will later enter with concepts of infinity, probability, and physical law. But before that, we stay with the human side. Why does the idea of literal repetition feel so different from symbolic cycles? One reason is our sense of self. We experience life not as a pattern, but as a continuity. We remember specific events with unique emotional tones. A particular morning, a particular loss, a particular joy. The suggestion that this exact stream might have played out before and will play out again can feel as if individuality is being absorbed into something mechanical. Yet the same thought can reverse in tone. It can feel as though existence has deemed your particular sequence of experiences worthy of repetition, as though reality itself has written your life into its underlying script. The emotional response depends on how we relate to our own story, and on whether we view repetition as imprisonment or affirmation. Ancient myths and philosophies did not resolve this tension, they simply held it. Time is cyclical, they said. Life returns, worlds return. Within that vision, some found solace. Others found challenge. And beneath it all, the fundamental observation remained. From the turning of galaxies, to the turning of seasons, to the turning of human fortunes, repetition is woven into the fabric of experience. Eternal return, in its oldest forms, is the recognition that the universe does not appear to move in a straight line. It circles, it spirals, it revisits themes, and invites us to consider the possibility that our own lives are entangled in patterns far larger than we can see. As you rest with these thoughts, you can imagine yourself standing at the edge of a very slow wheel. The wheel is time. On its surface are stars, worlds, lives, civilizations, all moving, all changing, and yet all part of a motion that curves back toward itself. You cannot see the entire circle. You can only sense that the motion is not purely linear, that somewhere beyond your horizon there may be a return. This image has guided human reflection for as long as we have watched the stars. It tells us that the idea of eternal return did not arrive suddenly from abstract theory. It grew slowly from the lived experience of cycles, day and night, seasons, life and death, rise and fall. From this soil, mythologies blossomed, philosophies developed, and later scientific questions emerged, all asking in their own language whether reality merely flows forward, or whether in ways we are only beginning to glimpse, it also returns. When we hear the word infinity, it can sound abstract, almost decorative, like a symbol at the edge of mathematics rather than something real. But in cosmology, infinity is not just a symbol. It is a question about the actual size and structure of reality. To understand why repetition might emerge from an endless cosmos, we have to move slowly through two ideas. How many possible arrangements the universe can have, and how much space and time it has to explore those arrangements. Imagine first the idea of a state. A state is simply a way the universe can be at a given moment. The positions of particles, the energy they carry, the values of fields, the configuration of matter and radiation, all of these together describe a physical state. Even without writing equations, we can ask a clear question. Are there infinitely many possible states, or only finitely many, at least in some region, with fixed energy and volume? Surprisingly, many physical models suggest that if you confine matter and energy to a finite region with a finite amount of energy, the number of distinct macroscopically meaningful states is not infinite. That does not mean the universe is simple. It means that when you look at it at a coarse enough level, where you do not track every tiny microscopic variation, you can classify its possibilities into a very large but potentially finite collection of patterns. You can think of this like pixels on a screen. If your screen has a fixed number of pixels, and each pixel can only show one of a fixed number of colors, then the number of possible images is enormous, but still finite. You could never finish looking at them all, but there is a definite count. Now imagine not a screen, but a region of space filled with particles obeying the laws of physics. If you restrict the energy and the volume, you can roughly view its configurations in an analogous way. You have a finite resolution set by quantum limits, and a finite amount of energy to distribute among those possibilities. The number of physically allowed arrangements may be extraordinarily large, so large that it exceeds any ordinary intuition, but it may still be finite. Now pair this with a second idea. Suppose space itself is not finite. Imagine a universe that extends without boundary in every direction, or a multiverse in which new regions continue to form forever. You then have a potentially infinite arena in which those finite types of states can appear. This is the core tension, a finite menu of possible local arrangements spread across an unbounded or effectively unbounded cosmic volume. In such a situation, probability begins to do something remarkable. When you have a finite set of possibilities and infinitely many places or times in which they can occur, repetition is not unlikely. It is guaranteed. This is the same logic behind a familiar analogy from probability. Imagine a library with an infinite number of bookshelves. On each shelf there is a book, and every book is the same length, the same number of pages, the same number of characters. You now fill each book with letters according to some rule, perhaps randomly with equal probability for each letter. How many different books are possible? Because the length is finite and the alphabet is finite, the number of distinct books is astronomically large, but still finite. Yet the number of books you actually have in the infinite library is infinite. In that setting, some book must occur more than once. In fact, each possible book will occur infinitely many times. There will be copies scattered through the library, exact repeats with every letter the same. The library is so vast that there is no way to avoid repetition. The only thing you could do to prevent it would be to forbid infinity itself. Now replace books with regions of space, replace letters with particle configurations, and replace shelves with galaxies or causally separated patches of the universe. Under similar reasoning, an infinite cosmos with a finite set of allowed local states would contain repetitions, possibly very many repetitions. This leads to the idea sometimes called the cosmic doppelganger. If the universe is spatially infinite and uniformly filled with matter and radiation, then somewhere beyond any distance you could realistically reach, there might be a region of space almost indistinguishable from the one around you now. A planet like Earth orbiting a star like the Sun, with continents, oceans, and perhaps even beings like you. Pushed to its extreme, the logic suggests that there could be regions where the configuration of particles matches our own region to arbitrary precision. Same physical laws, same initial conditions, same history. In those distant regions, a person could be sitting or lying down, having this same thought, wondering whether reality repeats. This is not presented as a certainty, but as a consequence of combining a finite set of local possibilities with a truly infinite volume. Here we meet a crucial distinction. There is a difference between mathematical inevitability and physical feasibility. Mathematically, if you declare that the universe is infinite and that local states are limited in number, then repetition becomes built into the framework. But physically, we do not yet know with confidence whether the universe meets those assumptions. We do not know with certainty whether space is infinite or just very large. We do not know precisely how many distinct states a region of space can occupy once all quantum effects and gravity are fully accounted for. We do not know whether the large-scale structure is uniform enough for the simple analogy to strictly apply. So while mathematics whispers that repetition is inevitable in an infinite cosmos, physics answers more cautiously. It says if the universe has certain properties, then these conclusions follow, but we have not yet measured all of those properties. Nevertheless, the exercise is illuminating, because it shows how repetition can emerge not from mysticism but from ordinary probability applied on a very large scale. We can deepen this picture by thinking in terms of probability spaces. In everyday life, a probability space is just the set of all outcomes that could occur together with rules assigning each outcome a likelihood. Roll a die and the probability space has 6 outcomes. Now extend this idea to cosmology. You can imagine a space of all possible configurations of some region of the universe. Each configuration is a point in this abstract space. As time evolves, the actual state of the region moves through that space following the laws of physics. Under some conditions, this motion can resemble a long, complicated walk, visiting many different states. If the system is ergodic, a term from statistical mechanics, it means that over a very long time, the system explores all accessible states in a way that reflects their underlying probabilities. You do not need to use the technical definition to grasp the basic point. Given enough time, a system with finite energy and confined volume might wander through almost all states available to it, and if it wanders long enough, it may revisit states it has seen before. Statistical mechanics uses this intuition to explain why macroscopic systems like gases in a box settle into equilibrium. There are many more states that look disordered than states that look ordered. So as the system wanders, it spends most of its time in disordered configurations. Now, if you combine this temporal wandering with the spatial vastness discussed earlier, you arrive at a picture where repetition in time and repetition in space are both possible. A single region of the universe could evolve long enough to revisit earlier states, and an infinite array of regions could instantiate similar or identical states in parallel. All of this emerges from the union of finite state spaces and large or infinite arenas of evolution. To clarify further, we can distinguish 2 different infinities that sometimes arise in these discussions. One is an infinity you can enumerate in principle, like counting the whole numbers 1, 2, 3, and so on. You could keep going forever, but each step is discrete. Another kind of infinity appears when you consider all the points on a continuous line between 0 and 1. There are so many such points that you cannot list them one by one, even in principle. In mathematics, these 2 infinities are said to have different sizes. But for our purposes, what matters is not the technical distinction, but the idea that some infinities are vastly richer than others. When we talk about possible configurations of space and matter, we are usually dealing with an effective finiteness in some region, because quantum and gravitational limits seem to restrict how much information can fit into a given volume. When we talk about how many times those configurations can be realized across an unbounded cosmos, we are playing with a different kind of scale, one that may be limitless. The combination is what drives the intuition that repetition must occur if the arena is infinite. Yet again, we have to be careful. These arguments rely on idealized assumptions: perfect uniformity, perfectly defined state counts, and a universe whose structure matches the models. Reality may be more subtle. Our actual universe might be finite in size or finite in effective volume due to curvature or global topology. It might have properties that prevent certain configurations from ever arising. Or it might have features we do not yet understand that alter the counting of states. So when we say that patterns must repeat in an endless cosmos, we are speaking conditionally. If the universe extends without bound, and if the local state space is finite in the relevant sense, then repetition follows. The logic is clear, but the premises are still under investigation. Nevertheless, the picture has power. It suggests that if reality is truly unbounded, then the idea of uniqueness at large scales may be an illusion. At human scales, each experience feels singular. Each moment seems to arrive once and vanish. But in a profoundly large universe governed by stable laws, the kinds of moments that arise may be limited in variety, and over long distances and long times they may recur. From a scientific perspective, this is an expression of combinatorics and probability. From a more contemplative perspective, it is a gentle shift in how we view our place in the cosmos. We go from imagining ourselves as part of a universe full of completely unique configurations to imagining ourselves as part of a universe where patterns repeat, where the local details of a life might be one instance of many scattered across space or across cycles of time. This does not diminish the felt reality of your own experience. You are still this particular instance with this particular stream of thoughts and sensations, but it hints that at the deepest level, the universe may play with a finite set of structural themes, rearranged and replayed enormously many times. When we combine the mathematics of large numbers with the possibility of infinite extent, we arrive at a quiet conclusion. If the universe truly has no boundary, and if its local possibilities are limited in number, then eventually patterns must repeat, not because of fate or design, but because in an endless arena, probability cannot help but circle back on itself. If you watch a glass fall and shatter on the floor, you never expect to see the fragments gather themselves, rise up, and assemble back into a perfect glass. Nothing in the basic equations of motion absolutely forbids this. The atoms could in principle move in just the right way to reverse the process. But in practice, you know it does not happen. This everyday intuition reveals something profound about time. There is a direction that feels natural, a before and an after. We remember the glass before it broke, but never a memory of it reassembling. This directionality is what we call the arrow of time. To understand it, we have to talk about entropy. Entropy is a measure of how many ways a system can be arranged while still looking the same at a coarse level. Imagine a deck of cards. If the deck is perfectly ordered from one suit to another, we call that a low entropy arrangement. There are relatively few ways to be perfectly ordered. But if the cards are shuffled thoroughly, the deck can be arranged in an enormous number of ways, all of which look like random shuffling to you. That messy state, highly disordered, has far more possible arrangements. Entropy in this simple picture is higher when there are more microscopic ways to realize the same macroscopic appearance. The same idea applies to a gas in a box. If all the gas molecules start off confined to one corner, that is a low entropy state. There are relatively few ways to have all the particles bunched in one region. As time passes, the molecules move and spread out, exploring more of the box. There are many more ways for the gas to be roughly uniform through the volume than there are ways for it to stay crowded in one corner. So overwhelmingly often the gas evolves from a special low entropy configuration to a typical high entropy one. You never see the opposite. This everyday observation is captured in the second law of thermodynamics. It says that for an isolated system, one that does not exchange energy or matter with its surroundings, entropy tends to increase or at least not decrease. This tends to is important. The law is statistical, not absolute. It is overwhelmingly likely that entropy increases with time because there are vastly more high entropy configurations than low entropy ones. The laws governing the microscopic particles, electrons, nuclei, fields can often be written in a way that does not care about the direction of time. If you reversed all the motions, the equations would still hold. At that tiny scale, time symmetry is common. Yet at the macroscopic level, you see a clear arrow. Things mix, spread, decay, and rarely, if ever, unmix, unspread, undecay. The difference is not in the fundamental laws, but in the counting. In how many ways order can exist compared to disorder. Low entropy states are rare. High entropy states are common. Once a system wanders into a high entropy region of its space of possibilities, it almost never finds its way back into a delicate arrangement like the original one. Not because it is impossible, but because it is so improbable that waiting for it to happen would take mind-stretching amounts of time. Now take this intuition and lift it from glasses and gases to the universe itself. On large scales, the cosmos can be treated as a physical system. It has matter, radiation, gravity, and possibly other components, all interacting, all subject to physical laws. We can ask what entropy means for such a system. Early in its history, the universe appears to have been hot, dense, and surprisingly uniform. Small fluctuations existed, but on large scales matter and radiation were distributed very evenly. Paradoxically, this nearly uniform state had low gravitational entropy. Because under gravity, a highly clumped universe full of black holes and collapsed structures represents a far higher entropy state than an almost perfectly smooth one. Over billions of years, matter has clumped, forming stars, galaxies, clusters, and filaments. Black holes, regions where gravity is so strong that not even light escapes, are believed to carry enormous amounts of entropy. From a gravitational perspective, the universe has been evolving from a low entropy beginning toward higher and higher entropy states. If you project this trend forward far beyond the lifetimes of stars, you arrive at what is sometimes called the heat death scenario. In that distant future, stars exhaust their fuel and go dark. Matter may decay or be swallowed by black holes. Black holes themselves slowly evaporate over inconceivably long periods by emitting radiation. Eventually, if this picture holds, the universe becomes a thin, cold bath of particles and radiation smeared out almost uniformly. No large-scale gradients, no significant free energy left to drive complex processes. This would be a very high entropy state. From the standpoint of the arrow of time, the story is from low entropy to high entropy, from an ordered beginning to a state where structure is diluted and change slows dramatically. At this point, you might ask if the arrow of time is tied to entropy, and if entropy tends to increase, could a universe ever see a reversal? Could it fluctuate back into a lower entropy configuration by sheer chance? In principle, yes. In a finite system that has reached equilibrium, there is always some tiny probability that random fluctuations carry the system from a typical high entropy state back into a more ordered one. This is extremely unlikely, but given enough time, almost any allowed fluctuation can occur. This is where the idea of rare fluctuations enters the picture. In statistical mechanics, you can compute how likely it is for a system to spontaneously move against the typical flow from disorder to order. For everyday systems with many particles, these probabilities are so small that you never see them. The gas in a room will not spontaneously gather into a corner. But if you imagine truly immense timescales far larger than the current age of the universe, you can talk about such fluctuations in principle. The Austrian physicist Ludwig Boltzmann used this kind of reasoning to explain why we see an arrow of time at all. He argued that entropy increase is simply the overwhelmingly likely behavior of systems that start in a low entropy state. Given many more high entropy states than low ones, the system drifts statistically toward those larger regions of possibility space. From this viewpoint, time's arrow is an emergent phenomenon. It is not that the fundamental equations insist on a direction. It is that the universe finds itself in a special configuration and then naturally evolves toward more typical ones. In this sense, time's flow is statistical. At the smallest scale, the basic laws may be mostly indifferent to direction. But at the scale of galaxies and glasses of water, probabilities are so unbalanced that one direction becomes effectively fixed. Forward from low entropy to high entropy, this statistical view has deep implications for recurrence. If a system spends an enormous amount of time wandering through its allowed states, and if its trajectory is such that it effectively explores the space of possibilities, it might, in unimaginably long periods, come arbitrarily close to some earlier configuration. However, the timescales associated with such recurrences are typically far beyond anything we can intuitively imagine. They can dwarf the current age of the universe by factors so large that numbers feel almost meaningless. Still, the conceptual point is clear. The arrow of time as we experience it is tied to the universe's position in its space of possible configurations. It might have been different if the early universe had been different. And in principle, rare fluctuations could create local pockets where entropy decreases briefly, even within an overall trend of increase. One extreme extrapolation of this reasoning leads to the idea sometimes called a Boltzmann brain. If a high-entropy universe persists for inconceivably long times filled with random fluctuations, one can ask what is more likely: a fluctuation that recreates an entire low-entropy universe, much like ours, or a smaller fluctuation that simply assembles for a short moment a single brain-like structure with coherent thoughts. Calculations in naive models can suggest that the smaller fluctuation is vastly more probable. If this were the dominant behavior of a very old cosmos, one could argue that typical observers should be such spontaneously assembled brains, rather than beings that arise gradually from the lawful evolution of a low-entropy beginning. This leads to a paradox. We do not feel like brief fluctuations with random memories. We perceive a long, stable history with consistent physical laws. The fact that our observations do not match the expectations from such scenarios is taken by many physicists as a sign that there is something incomplete or incorrect about applying naive fluctuation arguments to the entire universe. In other words, the thought experiment helps constrain cosmological models. A viable model should not imply that typical observers are brief, unphysical fluctuations in a nearly featureless sea. So even here, in the speculative edges of entropy and probability, the universe seems to push back against simplistic pictures. What remains clear is that entropy and the second law of thermodynamics give us a powerful lens for understanding time's direction. At the microscopic level, many processes are time-symmetric. If you could reverse every velocity and orientation, the equations would still work. At the macroscopic level, the enormous imbalance between the number of ordered states and the number of disordered ones creates a practical irreversibility. Broken glasses do not reassemble gases, do not spontaneously separate stars, do not unburn their fuel. The universe as a whole appears to be moving from an initially ordered state toward configurations with higher entropy. This does not forbid recurrence in principle. It simply tells us that any recurrence must operate within a landscape where overwhelmingly likely behavior is one-way flow. To imagine the universe like a system in a box that explores all its configurations and eventually returns, we have to balance two tendencies. On one side, the tendency of systems to wander through their space of states over very long times. On the other, the strong statistical bias toward high-entropy arrangements. These two together shape how we think about the possibility of cosmic recurrence. The arrow of time does not arise from a simple decree that time must flow forward. It emerges from counting from the geometry of possibility spaces, and from the special nature of the universe's beginning. At the smallest scale, time may not care which direction you choose, but at our scale, order collapses into disorder in a way so reliable that it defines our sense of past and future. As you rest with this thought, you can imagine the entire universe as a vast system exploring its own space of states. Clusters forming stars, igniting planets, cooling life, emerging, all part of the journey from low entropy to higher entropy. The arrow you feel in your own life, memories behind you, uncertainty ahead, is intertwined with that cosmic journey. Time's flow in your experience is not separate from time's flow in the cosmos. They are different scales of the same statistical story. And it is within this story of entropy and arrows that questions about recurrence must find their place. Imagine again a simple system, a box filled with gas molecules bouncing, colliding, moving freely. At any instant, you could in principle write down the positions and velocities of every molecule. That long list describes the state of the system at that moment. Now let the gas evolve. Molecules collide, change directions, transfer energy. The state moves from one configuration to another as time flows. You can imagine an abstract space, a kind of map where each possible configuration of the gas is a single point. This is sometimes called phase space. On this map, the evolution of the gas is like a trajectory, a path drawn through the space of all possible states. The French mathematician Henri Poincaré asked a precise question about such trajectories. Suppose you have a system with a fixed amount of energy confined to a finite region, and its motion obeys deterministic laws. If you look at the portion of phase space that the system can actually explore, it occupies a region whose volume is effectively finite. Now let the system evolve for a very long time. Its representing point moves through this region, never leaving it wandering along according to the equations of motion. Poincaré showed that under these conditions, the trajectory cannot spread out forever without eventually coming arbitrarily close to where it has been before. In simpler words, if a system has finite accessible states and evolves deterministically in a bounded way, then given enough time it will return arbitrarily near its starting configuration. This statement is known as the Poincaré recurrence theorem. It is a mathematical result about the structure of phase space trajectories in systems that satisfy certain assumptions. To make the intuition clearer, you can imagine a bead sliding without friction on the surface of a donut-shaped object, a torus. If the bead moves forever without leaving the surface, its path wraps around and around, tracing out a pattern. If the velocities are not chosen in a special way, the path may come extremely close to points it has passed before. Given unbounded time, the bead's trajectory on the surface will approach arbitrarily near any given point in the region it can explore. The gas in a box is far more complex, but the underlying idea is similar. The state of the system moves through a finite region of phase space. Under broad conditions, its trajectory must eventually wander back into the neighborhood of earlier states. Not necessarily exactly the same, down to every detail, but as close as you like, provided you are willing to wait long enough. The length of time you might have to wait is the difficult part. For macroscopic systems with enormous numbers of particles, the recurrence times predicted by this theorem are staggeringly large. If you tried to compare them to the current age of the universe's age would be like a moment, a fraction of a second, compared to spans of time so huge that ordinary language breaks down. You can think of it this way. Even though the number of states is finite, it is still vastly enormous. The system's trajectory in phase space has to weave through this vast set before coming close to where it began. The more particles, the more ways they can be arranged, the longer the expected recurrence time. For something like all the particles in a box of air, the recurrence time is so large that writing it as a number would not offer much intuition. This is crucial. The Poincaré theorem does not say that systems frequently or practically return to recognizable earlier states. It says that in principle, after an unimaginably long time, they will pass arbitrarily near those states. It is a statement about the geometry of trajectories under idealized assumptions. Now, why is this interesting for eternal return? Because it shows within the framework of classical mechanics that deterministic systems with finite accessible states are not endlessly novel. They do not explore an infinite variety of configurations. Instead, they must eventually revisit regions they have been in before. The motion is not a straight line through an unending landscape, but a complicated path inside a bounded region. If you project that path over unbounded time, recurrence is inevitable. This gives a mathematical foothold for the idea that physical systems might repeat themselves. But as always, there are conditions. The theorem assumes that the system is truly isolated. No energy or matter flow into it or out of it. Its total energy is fixed. It occupies a finite volume, and the allowed region of phase space associated with that energy is itself finite in measure. It also assumes that the motion is governed by time-reversible deterministic rules. These are reasonable approximations for some idealized systems, but they may not hold for the universe as a whole. The universe appears to be expanding. On very large scales, space itself is stretching. If the expansion continues indefinitely, the cosmos may not be described as a simple bounded system with fixed volume. Energy conditions, maybe subtle gravity and cosmic acceleration, are included. Quantum mechanics adds further complications. At quantum scales, the notion of a precise point in phase space is replaced by a more abstract object, a wave function, or a state in a Hilbert space. Some analogs to recurrence can still be formulated, but they depend on details of the spectrum of the system's energies and on how it is defined. So when we try to apply the Poincare recurrence theorem directly to the entire universe, we have to be careful. Our universe with gravity expansion, quantum fields, and perhaps dark energy may not satisfy the exact assumptions needed for the theorem. Even if some analog holds, the recurrence times would likely be so vast that for all practical purposes the cosmos appears irreversible. Still, the conceptual impact remains important. It shows that within physics you can derive recurrence behavior not by invoking cycles as a separate principle, but by analyzing the structure of state space and the nature of deterministic evolution. In this sense, the theorem opens a door. It says if reality, or some large part of it, behaves like such a system, then recurrence is not a mystical idea, but a mathematical consequence. However, it is crucial to separate recurrence of configurations from recurrence of conscious experience. When we say that a system's state returns close to where it began, we are talking about positions and momenta fields and energies within some approximation. To connect this to the repetition of a lived life is a further step. You would have to argue that the degrees of freedom encoding your brain, your body, and your environment are all included in such a system, and that their configurations return with enough precision that the same thoughts, perceptions, and memories unfold again. This is a much stronger claim. Even small differences in initial conditions can lead to diverging trajectories over time, especially in chaotic systems. So the recurrence theorem strictly applies to the full microphysical state of the system. If that entire microstate returns arbitrarily close, then in principle all macroscopic details, including patterns of neural activity, would be reproduced. But whether this happens for something as large and complex as the observable universe depends on whether the universe satisfies the needed assumptions. And we do not yet know that it does. Furthermore, the theorem is silent about personal identity. Even if a configuration identical to your current brain state appears again, either in the far future or in another region of a larger cosmos, we still have to ask what it means for that to be you. Physics can say that the pattern has reoccurred. It cannot by itself say whether the subjective I experienced that recurrence. These are questions that bridge physics, philosophy of mind, and metaphysics. From a strictly physical standpoint, the Poincare recurrence theorem lets us say this. In certain models, closed systems with finite accessible states and deterministic dynamics do not wander endlessly through a limitless variety of configurations. They eventually return arbitrarily close to previous configurations given enough time. The timescales are extraordinarily long, but not infinite for such recurrences. Applied naively to the universe, this can suggest that cosmic history might eventually revisit similar arrangements. But the naivety is important, because our real universe might expand forever, might not be strictly closed, and might have quantum and gravitational features that evade a straightforward application of the theorem. So we are left in a balanced position. On one side, we have a powerful mathematical result showing that recurrence is deeply rooted in the behavior of finite systems. On the other, we have the open question of whether the cosmos as we inhabit it actually fits that mathematical idealization. What remains for our quiet contemplation is the image of reality not as a one-way path through an infinite landscape, but as a motion confined to a structured region of possibility. A motion that might, in principle, trace near old paths again, not frequently not on human timescales, but on spans of time that stretch beyond ordinary comprehension. As you rest with this idea, you can imagine the state of the universe as a point wandering slowly through an immense but bounded space of possibilities. It circles, twists, loops, rarely if ever coming near an earlier position during ages that we can meaningfully imagine. Yet mathematically, over unbounded time, it does not simply drift outward into novelty forever. It remains contained within a cosmic chamber of allowed states. And within that chamber, paths can cross and recross at distances as small as one wishes, if one is willing to wait long enough. This picture does not guarantee that your life repeats, but it shows that recurrence is not foreign to the language of physics. It is a natural consequence of combining finite structure with unbounded time. Imagine the universe very early in its history, not filled with galaxies and stars and planets, but with something much simpler, a field spread almost uniformly through space. This field carries energy, and that energy does something surprising. Instead of behaving like ordinary matter or radiation, it acts like a form of constant pressure that drives space itself to expand faster and faster. This is the basic idea behind cosmic inflation. Inflation is a period of extremely rapid expansion proposed to explain several puzzles about the early universe. Why the universe looks so uniform in temperature in regions that seem too far apart to have communicated under ordinary expansion. Why the geometry of space appears so close to flat. Why there are no leftovers of exotic relics that some simple models might produce. By postulating that space underwent a brief episode of accelerated growth driven by the energy of a field inflation, can stretch initial irregularities to near uniformity. Small quantum fluctuations during this period can then be magnified into the seeds of cosmic structure, producing the pattern of tiny temperature variations we observe today in the relic radiation from the early universe. In its simplest versions, inflation is a phase that starts and then ends almost everywhere in roughly the same way. The field rolls down its energy landscape, inflation stops, and the stored energy is converted into particles and radiation in a process often called reheating. From that point onward, the universe expands more slowly, following the familiar hot Big Bang evolution. But certain models of inflation do something more. Instead of ending everywhere at once, inflation ends locally. In some regions, the field decays and expansion slows, creating bubbles, where a hot universe like ours can form. In other regions, the field continues, still driving expansion. Space in those regions keeps growing exponentially. Within that ever-growing inflating background, new bubbles can form. Each bubble is like a pocket universe with its own hot Big Bang phase, its own galaxies, its own evolutionary history. This process can continue without end. Even if inflation ends inside any given bubble, it persists elsewhere. As a result, the total volume still undergoing inflation can grow indefinitely. This is the core picture of what is often called eternal inflation. It produces not just one universe, but a vast ensemble of bubble universes. Some may have physical constants very similar to ours. Others may differ in the values of masses or interaction strengths, or in the detailed form of the low-energy laws that emerge after inflation ends locally. In some realizations, the number of such bubbles is effectively infinite, not simply large but unbounded. This is one route to what people call a multiverse. It is important to be precise. When we say multiverse here, we are not talking about independent realities arising from fictional devices, but about a physical mechanism within some theories of high-energy physics and cosmology. A mechanism in which inflation never completely stops everywhere, and in which new regions with hot Big Bang conditions are spawned continually. If the process continues indefinitely, the total volume of inflating space grows without bound. Within that ever-expanding backdrop bubble, universes like ours keep forming. Each bubble may itself be extremely large, possibly infinite in extent from the point of view of its own inhabitants. So you can end up with two levels of vastness. The interior of a single bubble can be huge, and the full ensemble of bubbles can be larger still. In such a setting, the notion of duplicate observers reappears. If the laws of physics within a given bubble allow a finite set of local configurations, and if the bubble is spatially infinite or very large, then the arguments about repetition from earlier apply again. In a single bubble universe with infinite spatial volume, there may exist regions where matter and energy organize into patterns indistinguishable from the region you occupy now. If eternal inflation forms infinitely many bubbles, some with similar properties, then across the full multiverse, the number of realizations of such regions can become immeasurably large. Not only duplicate planets, but duplicate histories may occur scattered through this ensemble. From a probabilistic standpoint, if you have a finite menu of possible local histories and unbounded space-time volume in which they can unfold, you expect repetition. This prospect leads naturally to anthropic reasoning. Anthropic reasoning is not about ego, but about selection effects. It asks, given that we exist as observers, what constraints does that fact impose on the kind of region we are likely to find ourselves in? In a multiverse picture, many regions might have physical constants or initial conditions that do not permit stable atoms, long-lived stars, or complex chemistry. In those regions, no observers arise, or at least not observers similar to us. In other regions, parameters fall within the narrow ranges that allow galaxies, stars, planets, and life. We should not be surprised to find ourselves in one of those rare regions because only there could beings like us emerge to ask questions in the first place. This line of thought does not explain why the multiverse exists or why its distribution of parameters has a given form. But it can explain why our observed universe has parameters that appear conspicuously hospitable to the development of complexity. Rather than treating this as an extraordinary coincidence, anthropic reasoning views it as a selection effect. In a landscape of many possible universes, we inevitably observe a universe compatible with our existence. Eternal inflation provides one framework in which such a landscape could be realized physically. Different bubbles could settle into different vacuum states with different effective constants and even different low-energy laws. Among that ensemble, only a subset supports observers. We inhabit one of those. Again, this is not a claim that such a multiverse definitely exists. It is a statement that certain theories naturally produce a structure where these kinds of arguments have to be considered. At this point, you might ask, does eternal inflation eliminate the need for a beginning? If inflation is eternal to the future, could it also be eternal to the past? Could the process have been going on forever with no initial moment? The question has been studied carefully. Under broad conditions, a group of researchers showed that if the average expansion rate along a given world line is positive, then you cannot extend that world line backward indefinitely. Instead, it must reach a boundary in finite proper time. This result is often summarized by saying that inflating spacetimes are past incomplete. In simpler language, even if inflation continues without end into the future, it likely cannot stretch without beginning into the past. Some sort of initial condition or pre-inflationary phase is still required. This does not tell us what that beginning looked like. Only that within certain assumptions, eternal inflation does not erase all traces of an origin. So we are left with a picture where the multiverse, if it exists, has both endless generation forward and some kind of boundary or special condition behind. Within that vast structure, regions like ours may arise many times. Some may resemble our cosmic history closely, others may differ from their earliest moments. In this context, the question of repetition becomes layered. First, at the level of space within a single bubble universe, there may be enough volume for configurations to recur if the state space is finite. Second, at the level of bubbles in an eternally inflating background, there may be huge numbers of separate universes, some with overlapping properties. Third, at the level of anthropic selection, only a subset of these regions contain observers capable of reflecting on such questions. In that subset, patterns of history may be repeated. The idea that there could be not just one version of you, but many scattered across an enormous multiverse, can feel either dizzying or strangely calm. From the standpoint of physics, what matters is not the psychological reaction, but the consistency of the underlying models. Do high-energy theories naturally lead to inflating states that reproduce themselves? Do the predicted patterns match what we observe in the detailed structure of cosmic radiation and large-scale clustering? Is the framework mathematically coherent and compatible with quantum gravity? These questions are still under investigation. Eternal inflation and the multiverse ideas remain active areas of research and debate. Some physicists view them as natural consequences of simple inflationary models. Others are cautious, concerned about testability and about how probabilities should be defined in an infinite ensemble. From the perspective of quiet contemplation, we can hold the picture lightly. We can imagine a reality in which our observable universe is one region within a far larger structure, a structure where inflationary expansion keeps generating new domains, each with its own cosmic story. In some, no galaxies form. In others, galaxies abound, but conditions are too violent for life. In a few, the balance of forces and parameters permits long-lived stars, rocky planets, water chemistry, and eventually minds that look up and wonder. Among those minds, some consider the possibility that their lives are not singular, but one instance of a pattern that repeats. The mathematics of large ensembles and infinite volume does not decide questions of meaning. It simply says that in a sufficiently vast reality, events compatible with the laws of physics will occur not just once but many times. You are still this particular realization of a conscious observer in this particular region with this particular history. But the multiverse picture gently suggests that the broader fabric in which you are woven may be far larger than the region you can see. And in that fabric, if inflation is eternal, and if the multiverse is real, the question arises softly. If infinite universes exist, how many times might you appear? Imagine the universe not as a story with a single beginning and a single end, but as a breath, a long, slow cosmic inhalation followed by an equally long cosmic exhalation. Space expands, then contracts. Galaxies drift apart, then fall back together. Temperatures drop, then rise. The entire cosmos moves through phases, the way a living being moves through its own rhythms. This is the guiding picture of cyclic cosmology. Instead of a universe that starts once in a singular beginning and then expands forever, cyclic models propose that the universe may undergo repeated phases of expansion and contraction, a cosmic cycle in which each round is like an era, a chapter in a much larger book. To see how this idea arises, it helps to go back to the simplest descriptions of cosmic evolution. In standard cosmology, the geometry and dynamics of the universe can be approximated by treating it as a homogeneous and isotropic fluid on large scales. The equations that govern its expansion tell us how the scale factor, a quantity that measures the relative size of the universe, changes with time. Depending on the average energy density and the curvature of space, different behaviors are possible. In some solutions, if the density is high enough, expansion slows, stops, and reverses. The universe reaches a maximum size, then begins to contract. Distances between galaxies shrink, temperatures rise, structures collapse. Eventually, in these models, the universe may end in a big crunch, a state of extreme density, somewhat mirroring the Big Bang from which it began. It is natural to ask if a big crunch could be followed by a new Big Bang. If the universe collapses to extreme density, could it bounce instead of terminating? Could the end of one cosmic phase become the beginning of another? This simple thought leads directly to cyclic cosmologies. In the earliest versions, the idea was relatively straightforward. A closed universe expands from a hot, dense state, slows, reverses, contracts, and ends in a crunch. Then somehow from that final state, a new expansion begins. The details were often left unspecified. The focus was on the possibility that the universe does not exist only once, but passes through eternal sequences of expansions and contractions. Later models attempted to give more specific mechanisms for the bounce. In some proposals, quantum gravitational effects become important when densities are extremely high. Those effects modify the classical equations, so that instead of hitting a singular point where quantities diverge, the universe undergoes a transition. A contraction phase reaches a minimum scale, then reverses into a new expansion. This is the essence of a quantum bounce. Loop quantum cosmology, an application of loop quantum gravity ideas to the universe as a whole, provides one framework where such bounces are studied. In this approach, space itself is treated as having a discrete structure at very small scales. When you apply this discrete geometry to the very early universe, the classical singularity can be replaced by a high-density regime where quantum corrections generate a repulsive effect. Instead of densities blowing up to infinity, they reach a large but finite maximum, and the universe rebounds. On one side of the bounce lies a contracting phase. On the other side, an expanding phase. The story can support the idea that what we call the Big Bang may have been a transition point from a previous cosmic era of contraction. If such bounces can occur repeatedly, you have a natural path to cyclic cosmology. Each cycle contains an expansion phase with structure formation followed by some process leading eventually to contraction and then a new bounce. Another class of models approaches cyclic behavior from a different angle. In theories with extraspatial dimensions, our visible universe may be described as a three-dimensional brain embedded in a higher dimensional space. In ekpyrotic models, two such brains can slowly move toward each other in the higher dimensional space. Their eventual collision releases energy which appears to observers on the brain as a hot Big Bang. After the collision, the brains move apart, the universe expands and cools. Over immense timescales, they may again slowly move toward each other, preparing for another collision. Each approach, each brain encounter, can correspond to a new cosmic cycle. This ekpyrotic picture offers interesting benefits. The phase in which brains approach can generate conditions that smooth out the universe and create the seeds for structure in a way that differs from standard inflation, but aims to achieve similar results. The word ekpyrotic comes from a Greek term associated with cosmic fire and periodic destruction and rebirth. In these models, our Big Bang is not the absolute beginning of all things, but one event in an ongoing sequence of brain interactions. The expansion history we observe is just one chapter in a longer, higher dimensional story. Other cyclic models combine ingredients from quantum gravity and effective fields in different ways. Some propose that dark energy or other components change over time, driving phases of acceleration and deceleration that can lead to contraction. Others explore how entropy behaves across cycles. Here we meet a subtle challenge. In standard thermodynamics, entropy tends to increase. If the universe simply cycles expanding and contracting over and over, and entropy always grows, then each new cycle would contain more entropy than the last. That could make cycles progressively longer and more dilute. Eventually, structure formation might be suppressed. To maintain a truly repeating cosmos, some models need a way to reset or dilute entropy between cycles. In ekpyrotic scenarios, the long period of slow contraction before each bounce can smooth and thin out certain forms of energy and structure. In some quantum bounce models, the density and content of the universe at the bounce may be such that information from the previous cycle is not fully preserved in accessible form. The details are technical, but the conceptual point is that entropy and information must be carefully handled if cycles are to continue indefinitely without each one becoming radically different. This leads naturally to deeper questions. Does information survive cycles? If a universe contracts, does it carry a detailed record of all previous events into the next expansion? Or is that record effectively erased or scrambled so thoroughly that the new cycle has no practical memory of what came before? Some formulations of cyclic cosmology lean toward the idea that only broad properties survive. The overall laws of physics, the general behavior of large-scale geometry may persist, but the detailed arrangement of galaxies, stars, planets, and individual lives does not. Each cycle has its own structures, its own histories. In this view, cycles are similar in their governing rules, but different in their specific outcomes. Other more speculative ideas leave open the possibility that certain patterns could echo from one cycle to the next, perhaps not as precise copies, but as statistical imprints encoded in subtle correlations. At present, we do not know. Cyclic models are diverse, and the question of how much information can cross a bounce remains an area of active research. From the perspective of eternal return, this is crucial. If information were preserved with extreme fidelity, then a sufficiently exact bounce might lead to very similar or even identical histories unfolding again. If information is largely washed out, then each cycle is more like another roll of cosmic dice following the same rules but generating new detail. The difference between a universe that replays and a universe that rethemes rests partly on how entropy and information move across the bounce. Another question concerns identity. Could identities repeat across cycles? If a cycle unfolds according to the same laws and perhaps similar initial conditions, could there exist a later cycle in which a planet much like Earth forms again, life evolves again, and a person with your genetic makeup and environment appears again? In a broad sense, this is similar to the earlier discussions about infinite space. If the space of possible configurations is finite and cycles are numerous, then repetition at some level is statistically encouraged. But whether such a recurrence would be you raises familiar questions. Even if a future cycle contained a person with the same brain structure and memories as you have now, we still confront the issue of subjective continuity. Does subjective identity require an unbroken physical path through time? Or is identity merely the pattern? If it is the pattern, then a new cycle reconstructing that pattern could be viewed as reinstantiating you. If it requires continuity, then each cycle's version is a new observer, a separate center of experience, even if structured identically. Physics by itself does not answer this. It can describe whether configurations repeat. It does not settle whether the subjective I persists across cycles. From a calmer vantage point, you can hold both possibilities lightly. On one hand, cyclic cosmology might imply that structural echoes of present experiences appear again in distant cosmic epochs. On the other, the meaning of personal identity may be such that each echo is its own distinct subject. Either way, your lived experience now remains uniquely yours in this cycle. Another theme in cyclic models is the question of whether events are reset. Does a new cycle start fresh with no memory and no remnants, or does it carry subtle traces of what preceded it? Some proposals suggest that certain forms of radiation or scalar fields could carry information from one cycle to the next. Others suggest that the violent conditions near the bounce overwhelm most detailed structure. From an observational standpoint, cosmologists look for signatures in the large-scale distribution of galaxies or in the fine details of the cosmic background radiation that might favor or disfavor certain cyclic models. So far, no definitive evidence has selected a single scenario. Cyclic cosmologies remain intriguing possibilities rather than established descriptions, yet they offer a conceptually rich framework. They allow us to imagine a universe that does not simply appear once and fade, but instead undergoes repeated epochs of structure and dissolution. Each cycle is vast from our perspective, billions of years of star birth planet formation and evolution. Yet compared to the endless sequence of cycles, each one is only a chapter. A universe breathing in and out, expanding, cooling, complexifying, then contracting, heating, simplifying, and bouncing. From the quiet perspective of a listener at rest, this image can be strangely soothing. It suggests that the cosmos is not a one-time event, but an ongoing process. A process in which creation and destruction are not absolute opposites, but phases in a larger rhythm. Whether or not our universe actually behaves this way, we can appreciate the scientific care with which such models are constructed. They are not mere stories, but attempts to extend known physics into regimes of extreme density and curvature. To ask how general relativity and quantum theory combine when the universe is at its most compressed, and to see whether those theories permit a graceful passage from one cosmic era to another. In contemplating cyclic cosmology, we are reminded that the universe may have structures of time far beyond our immediate experience. Human lives are brief pulses set against timelines of stars and galaxies. Those stellar and galactic eras may themselves be only episodes within larger cosmic cycles, time layered within time, rhythms nested inside greater rhythms. As you rest with these thoughts, you can picture the universe as a vast ocean. On its surface, waves rise and fall, short-lived patterns of motion and foam. Beneath that, tides slowly rise and recede. Beneath even that, there may be deep currents circulating over ages. Cyclic cosmology invites you to imagine those deepest currents on the scale of the cosmos itself. Not just one event, but a series perhaps without end. In that broader view, episodes of expansion and contraction are simply part of how reality moves. Whether information survives intact, whether identities repeat, whether events are reset, are questions that remain open. But the framework gives a scientific language for exploring them. And as you drift toward quieter states of mind, you can allow this possibility to occupy a soft place in your thoughts. A universe that does not simply begin and vanish, but breathes, again and again and again. Imagine the universe not only as a sequence of cycles, but as a chain of worlds, each world so vast in time that it feels complete in itself. Each world has its own galaxies, its own stars, its own history, from a hot, bright origin to a cold, dilute end. Roger Penrose, a mathematical physicist, proposed a framework in which such worlds called aeons follow one another in an endless succession. Each aeon is a full universe from its earliest moments to its ultimate future. The surprising idea is that the remote future of one aeon can be reshaped into something that looks mathematically similar to the very beginning of the next. To understand how this might be possible, we have to look closely at the ingredients of the far future. In many standard cosmological models, our universe continues to expand, driven partly by a component that behaves like dark energy. As time passes, galaxies that are not gravitationally bound to each other move farther and farther apart. Stars burn through their fuel and go dark. Black holes formed from massive stars and from dense regions of galaxies dominate the massive structures. Over extraordinarily long timescales, black holes themselves are expected to lose mass through a process known as Hawking radiation. Quantum effects near the event horizon allow pairs of particles to form with one falling in and one escaping. From the point of view of an external observer, the black hole slowly radiates energy and gradually evaporates. For supermassive black holes, the timescales involved are enormous, much longer than the current age of the universe by factors beyond ordinary comprehension. But if you wait long enough in this picture, even these great engines of gravity eventually dissolve. What remains after black holes evaporate and stars fade is a universe dominated by low-energy radiation and extremely light particles drifting through ever-expanding space. Massive particles become increasingly rare, and the energy scale drops and drops. In this remote future, the universe tends toward a state where almost no structures remain. No galaxies, no stars, no black holes. Just a thin bath of nearly massless quanta spreading across a vast geometry. At such low energies, the distinction between time and space becomes less meaningful in certain mathematical descriptions. Penrose noticed that in this asymptotic regime, the physics can be described in a way that cares more about angles and shapes than about absolute scales. This is the language of conformal geometry. A transformation is called conformal if it preserves angles while allowing distances to be stretched or compressed. You can imagine taking a picture and rescaling different regions, making some parts larger, some smaller, but keeping the local shapes intact. In conformal descriptions, overall size loses importance. Only the structure of light-like paths and the relationships between directions really matter. Penrose's idea in conformal cyclic cosmology is that the very late universe of one aeon can be mapped through a conformal transformation to look like the very early universe of the next. At first, this seems impossible. The late universe is enormous in size, cold and thin. The early universe is tiny, hot, and dense. How could one be reshaped into the other? The key is that in the remote future, when only massless particles remain, there is no intrinsic scale built into the physics. Massless particles such as idealized photons do not carry an internal clock defining a preferred timescale. They travel along light-like paths, and their behavior can be described purely in terms of angular structure. If all massive particles disappear and only massless ones remain, then according to this idea, the universe can be described in a conformally invariant way. In such a description, you can rescale distances and times by large factors without changing the essential physics. Penrose proposes to use this conformal freedom to compress the vast future of one aeon into a boundary surface and then reinterpret that boundary as the bang-like beginning of the next aeon. In this picture, each aeon begins with a hot, dense phase where particles may be effectively massless due to extremely high energies. As the aeon evolves, particles acquire mass structures, form galaxies, and black holes appear, and complexity grows. Eventually, over immense periods, massive particles decay, black holes evaporate, and the universe again approaches a state dominated by massless radiation. At that stage, the conformal description becomes relevant again. You can then forget about overall scales and represent this end state as a new beginning. The end of one aeon is sewn mathematically to the beginning of the next. This sewing is not physical collision or bouncing in the usual sense. It is a matching of geometries across a conformal boundary. The entire history of each aeon occupies a wedge in a conformal diagram. The future boundary of one wedge is attached to the past boundary of the next. In this way, an endless succession of aeons forms a chain, each linked to the next by conformal matching. Within each aeon, physics follows the familiar rules of general relativity and quantum field theory, as far as they are known. The novelty lies in how aeons connect, and in the assumption that massive degrees of freedom eventually disappear. Black hole evaporation plays a central role. Black holes not only contain enormous entropy but also act as sinks for information. In conformal cyclic cosmology, their complete evaporation helps ensure that the late universe is dominated by massless particles, which is necessary for the conformal stretching. There is also a subtle question about information transfer. If black holes evaporate by emitting radiation, does the pattern of that radiation encode information about matter and events that fell in? This ties into the black hole information problem. Some approaches to quantum gravity suggest that information is not destroyed, but is somehow encoded in the outgoing radiation or in correlations within the complete quantum state. If such encoding occurs, then in principle, the very late universe contains traces of past events spread out in its radiation field. Penrose has proposed that certain signatures of processes very late in a previous aeon could leave faint imprints on the early conditions of the next. One specific suggestion is that extremely energetic events involving supermassive black holes in the previous aeon might produce patterns that carry through the conformal matching. As the geometry is rescaled, these patterns could appear as subtle features in the radiation of the new aeon's early universe. In our aeon, the relic radiation from the hot early phase is the cosmic microwave background. It is remarkably uniform, but contains small fluctuations in temperature at the level of tiny fractions of a degree. Penrose and collaborators have argued that within this background there may be concentric circular features, regions where temperature variations are unusually low compared to surrounding areas. They have suggested that such circles could be interpreted as evidence of energetic events, such as black hole encounters in a preceding aeon, whose signatures survived through the conformal mapping. Other researchers have examined the same data and reached different conclusions. Some studies find that the claimed patterns are consistent with random fluctuations. Others argue that the statistical significance is not strong enough to count as clear evidence. At present, the situation remains unresolved. Conformal cyclic cosmology is an active but speculative proposal. It is taken seriously enough to be analyzed and critiqued within the scientific community, but it has not been confirmed. This is important. The idea of successive aeons connected by conformal geometry should be viewed as a possible framework, not as an established description of reality. Part of its appeal is conceptual. It offers a way to address the question of what came before our observable Big Bang. Instead of a single origin from absolute nothingness, it replaces the bang with a boundary between aeons. Our beginning is someone else's end, and our end may be the beginning of another. It also provides a different angle on the puzzle of low initial entropy. In standard cosmology, the early universe appears to have had a remarkably low gravitational entropy. Penrose's framework attempts to link this low entropy start to constraints imposed by the conformal matching with the previous aeon's end. The requirement that the future geometry be stretchable into a smooth boundary may force conditions that manifest as low initial gravitational entropy in the next aeon. Whether this mechanism ultimately works in full detail remains an open question. From the perspective of eternal return, conformal cyclic cosmology gives yet another way for the universe to exhibit repetition. Each aeon has its own history, but the overall pattern of an aeon's birth and death repeats. Hot beginning, structure formation, black holes, and long decay to a radiation-dominated fade. Then through conformal matching, a new aeon begins with similar large-scale structure of laws. Are the aeons identical in every detail? Most likely no. Quantum fluctuations and chaotic dynamics would ensure that specific arrangements of matter and events differ aeon to aeon. But in broad outline, the sequence of global phases might be similar. This is different from a simple cyclic universe that expands and contracts in the same spacetime. Here each aeon is its own spacetime region with its own metric linked to others through conformal boundaries. The repetition is at the level of structural pattern rather than exact replay. You can think of it like a musical form. The same structure recurs movement after movement, but the detailed notes, their timing, their emphasis may differ each time. In this way, conformal cyclic cosmology sits at an interesting intersection. It uses advanced mathematics to propose a concrete mechanism for an eternal sequence of universes. It allows for the conceptual possibility of faint echoes from previous aeons appearing as subtle patterns in our own. At the same time, it remains fully aware of the limits of current evidence. As you rest with this idea, you might picture not just one cosmic cycle, but an unending chain. Each aeon like a vast luminous bead on an infinite string. Inside each bead, galaxies flash into existence, live their long lives and fade. Black holes dominate, then evaporate. The contents blur into a nearly featureless sea of low-energy radiation. At that stage, size loses meaning. The geometry can be compressed without changing its essential causal structure. And in that compression, a new beginning is born. Seen from within, each aeon feels complete. Its inhabitants experience a single universe with a single cosmic history. They may debate how it began and how it will end, unaware that from a broader perspective their entire cosmos is one chapter in an endless narrative. Whether conformal cyclic cosmology is ultimately correct or not, it offers a gentle reminder. Our current universe may not be the whole story. The space and time we can observe could be one phase in a larger pattern, stretching beyond our horizon of comprehension. A pattern in which aeons succeed aeons each, leaving faint whispers in the one that follows. And within one of those aeons, on a small planet around an ordinary star, a mind lies down to rest and wonders whether this life, this universe is unique, or an echo, one of many in an infinite chain. Some questions only arise once the universe is allowed to be vast. Once you accept that space may be unbounded, that time may stretch far beyond any single human lifetime, and that patterns of matter and energy can in principle recur. Then a quiet but unsettling thought appears. If an identical copy of you exists elsewhere, is it you? And if time itself or cosmic conditions recur, do you recur? To approach this gently, we start not with the cosmos, but with something very close. The sense of I. Right now you experience a continuous stream of sensations, thoughts, and memories. This stream feels unified. When you remember yourself as a child, you treat that child as you. Even though the body, brain, and personality have changed, cells have died and been replaced. Molecules that once formed part of you now belong to the environment. Patterns of activity in your brain have evolved, and yet you feel a thread of identity linking your current experience to that earlier one. This simple observation already hides a deep fact. You do not define yourself by exact physical substance. You define yourself by continuity of process and memory. Your body is already a kind of ship of Theseus. Imagine a wooden ship. Over many years, every plank, every nail is gradually replaced. At the end, no original piece remains. Is it still the same ship? One answer is that identity lies in continuity of structure and function over time. The ship kept sailing through its repairs, its form and role remained coherent. By that standard, it is the same ship. A more strict answer is that once all components change, it becomes a different object. The debate persists because identity turns out to be less about physical atoms and more about how we choose to map patterns over time. Your body is like that ship. Atoms flow in and out, yet the structure and certain key patterns are maintained. Your brain is a dynamic network constantly rewiring, strengthening some connections, weakening others, but preserving enough continuity that you can tell a story about being the same person. So when we ask who you are, two pictures appear. One sees you as substance, a particular collection of matter. The other sees you as process, a pattern of organization, a flow of information implemented in matter but not identical to it. In everyday life, the process view matches experience better. If you lost some atoms, you would not feel that a different consciousness has taken over. But if your memories and personality were radically altered, you might feel that the you recognize has largely dissolved. From this perspective, you are more like a continuously updated pattern than a fixed object. Now carry this idea into a larger cosmos. Suppose that in another region of space or in a future cosmic cycle, matter arranges itself into a pattern identical to the detailed structure of your brain and body right now. Same configuration of neurons, same strengths of synapses, same sensory inputs at that instant. Would that being be you? From physics alone, what we have is a claim about pattern identity. This distant being has the same structure and the same internal information. If you scanned its physical state and compared it to your current one, they would match to within whatever precision you consider relevant. Subjectively, from the inside, that being would awaken with your memories, your dispositions, your sense of self. It would think, I am this person, with the same confidence you do. From the being's own point of view, it is you. From an external point of view, it is one instance of a pattern. But does your own consciousness continue into that being? This is where the distinction between pattern identity and subjective continuity becomes important. One line of thought says that continuity requires an unbroken sequence of physical states linked by causal evolution. In this view, you tomorrow are the result of you today through a continuous process. If somewhere else, a matching pattern is created independently, there is no causal bridge from your current brain state to that distant one. So even though the pattern is the same, it is a separate subject. Another line of thought says that what matters for identity is the existence of a particular pattern, not the path taken to realize it. In that view, if an identical brain state exists elsewhere, it instantiates the very same mind. The question, is it you, becomes almost a matter of convention. Do we reserve you for a single continuous chain in one world line, or do we allow you to refer to any instance of a certain pattern? Physics does not decide this. The equations describe how states evolve and how patterns can recur. They do not assign ownership of experience. In the context of eternal return, the same ambiguity arises. If time recurs, do you recur? Suppose that the universe or some subset of it evolves in such a way that after an enormously long time it returns to a configuration indistinguishable from its state now. The Poincare recurrence theorem suggests this is mathematically possible under certain assumptions. At that recurrence, the pattern describing you would appear again. A being with your memories, your character, your situation would exist again. From the inside, that being would feel like you. Yet from a viewpoint that tracks time as a continuous parameter, one could say that this is a new occurrence separated from you now by an immense interval. No continuous awareness passes through the ages like a single thread. Instead, we have two nodes, two instants containing the same pattern. Whether this counts as your life repeating or as a distinct life imitating yours depends on how you choose to define personal identity. Now bring in determinism and randomness. If the universe were strictly deterministic, every state would follow uniquely from earlier states. Given a complete specification of the universe, now its future and past would be fixed. In a deterministic world, if the same global state ever occurs again, its entire future would be the same. If a cosmic cycle recreates the universe with identical conditions, the events that unfold would mirror those of the previous cycle. Your life would play out in the same way again. In that setting, eternal return is literal. Each cycle repeats every detail, including your thoughts, choices, and feelings. In more realistic physics, quantum effects appear to introduce some degree of fundamental randomness. When a quantum system is measured, we can only predict probabilities for different outcomes. In many interpretations, these outcomes are not determined in advance by hidden variables. Instead, the universe contains genuinely stochastic events. If cosmic evolution includes such events, then even if large-scale conditions recur, microscopic differences could amplify over time. Histories in different cycles might diverge. Your life in one cycle could be nearly identical to your life in another, but not perfectly. A conversation here might differ by a sentence. A decision there might swing the other way. The general pattern might recur, but the fine detail could vary. This softens the notion of exact repetition. In some versions of quantum theory, such as the many worlds interpretation, every possible outcome of quantum events is realized in some branch. In that view, determinism is preserved at the level of the global wave function, but randomness reflects which branch a given observer inhabits. Here too, identities and recurrences become subtle. Copies of you exist in different branches, sharing history up to a branching event and diverging after. They are all structurally continuous with the earlier you, yet follow different futures. From the standpoint of eternal return, this paints a universe where patterns of identity spread across branching structures and possibly across cycles and regions. In every version, a central theme emerges. You are best understood as a pattern implemented in physical processes. The pattern includes your brain's structure, its connectivity, its functional organization, and the dynamic patterns of activity that give rise to experience. It also includes your memories, the way your nervous system encodes past events. Memory binds your current state to earlier states. Without memory, the sense of a continuous self would collapse. Each moment would be isolated. Instead, your brain records and updates. It integrates past information with present input. In doing so, it constructs an ongoing model of a self persisting through time. So identity in practice is anchored not just in physical pattern, but in memory continuity. If a perfect copy of you were created with all of your memories up to this moment, that copy would feel an unbroken continuity, stretching back. It would say, "I remember my childhood," with the same conviction you have. But from a global vantage point, two streams of experience exist. One continues in your current body, another begins in the copy. They share a past. They diverge in the future. If such patterns arise in distant parts of an infinite cosmos, or in distant cycles of a cyclic universe, we obtain many streams, each carrying the sense of I, each justified by their own memories. In that setting, the question, which one is really me, has no single answer. The pattern view suggests that all of them are equally valid instances of the same underlying structure. The continuity view assigns you to the particular chain of states that evolves from your current one. Neither perspective is forced by physics. Each is a way of projecting our intuitive notion of self onto a much larger canvas. From a meditative standpoint, this can be strangely calming. It lowers the pressure on uniqueness. The value of your experience does not depend on whether it happens once or many times. It does not depend on whether there are copies in distant regions or in future aeons. Right now, you are a locus of organized matter carrying a particular pattern of information. Your consciousness is the process of that pattern running. Whether or not that pattern reappears elsewhere does not change the immediacy of this moment. Seen this way, identity is less a solid object and more a wave of structure moving through matter for a time. In a vast cosmos with infinite volume or endless cycles, similar waves may arise many times. Each time a new I comes into being imbued with the feeling of continuity, each one authentic from its own point of view. The universe may not distinguish between originals and copies. It simply realizes patterns wherever conditions allow. You are one such pattern now. In a repeating cosmos, others like you may exist or may emerge, but the task of physics is to describe how such patterns can form and recur. The task of questions about who those patterns belong to lies partly beyond science. As you let these thoughts settle, you can release the need for a definitive answer. You are here in this configuration in this instant. Your memories form a continuous thread behind you. Your future forms an open fan of possibilities ahead. Whether similar threads have been woven before or will be woven again does not diminish the quiet depth of this particular strand. In a universe where patterns may repeat and cycles may return, you remain a unique perspective on reality, a viewpoint through which the cosmos is briefly aware of itself. There is a quiet boundary where human intuition stops being reliable. It is the place where numbers grow too large, where timescales stretch beyond imagining, and where probability no longer behaves like everyday experience. In this region, our minds tend to mislead us. We evolved to judge distance by how far we can walk, to judge time by days and seasons, to judge chance by small games, by weather patterns, by the regularities of ordinary life. We did not evolve to feel at home with infinities, or with probabilities that refer to unimaginably many universes, or to time spans so long that even stars seem short-lived. When we talk about eternal return, infinite space, or infinitely many cycles, we step directly into this region where intuition fails. Take infinity itself. In everyday language, infinite often feels like very large. But in mathematics, infinity is not a large number. It is a different kind of object. You cannot reach it by counting longer. There is no almost infinite. There are also different sizes of infinity. The set of whole numbers is infinite. The set of points on a line is also infinite. Yet the infinity of points on a line is in a precise sense larger than the infinity of whole numbers. These ideas already stretch our sense of quantity. Now combine infinity with probability. In ordinary life, if you repeat a fair coin toss a few times, you expect a mix of heads and tails. If you repeat it 1,000,000 times, you can use probability to estimate how often certain patterns occur. But if you imagine an infinite sequence of coin tosses, you encounter questions that cannot be answered by simple analogies. In an infinite sequence, every finite pattern you can write down will occur infinitely many times. The specific pattern that encodes your birth date in some code will appear not once but endlessly. Yet the probability of any particular finite pattern appearing right at the start is still very small. This is the tension. What is almost impossible locally becomes inevitable globally in an infinite setting. Our intuitions about what is likely are tuned to local contexts. They misfire when applied to infinite structures. When we say, in an infinite universe there will be copies of Earth, we are using this kind of reasoning. Locally, the chance of matter arranging into a specific planet with a specific history is unimaginably tiny. But if the volume is truly infinite and the rules allow it, even astronomically rare configurations become expected somewhere. The human mind is not built to visualize an infinite cosmic mosaic in which every allowed pattern occurs endlessly. We tend to import language from small number experience. We say things like, that seems too unlikely to happen even once, forgetting that in an infinite context, too unlikely changes its meaning. This gap between formal probability and human intuition is one reason cosmological arguments about eternal recurrence must be handled with care. It is easy to overinterpret what infinity implies, or to underinterpret it. Our second limitation comes from physics itself. Physics is incomplete. What we call the laws of nature are models, compact descriptions of regularities we have observed. They have been tested over impressive ranges of energy, distance, and time. But they are not final truths. We know, for example, that general relativity and quantum mechanics are each highly successful in their domains. Yet their unification into a single framework of quantum gravity remains unfinished. We lack a complete theory of what happens at the highest densities and smallest scales. We also lack direct observational access to most of the universe. We see a thin slice of its history. We can infer earlier states from radiation and structure, but we do not watch the full movie. We have no data from future epochs, and no direct measurements from other bubble universes if such things exist. We build models to cover these blind regions. Some models suggest eternal inflation. Some suggest cyclic cosmologies. Some suggest conformal chains of aeons. We test what we can. But many aspects of these models lie far beyond current experimental reach. So when we reason about eternal return, we are effectively stacking uncertainties. We start with incomplete physics. We extrapolate it into regimes where we have never tested it. Then we combine those extrapolations with arguments about infinity and probability, which already challenge our intuition. None of this means such reasoning is worthless. It simply means we must hold conclusions lightly. Another source of limitation comes from measurement itself. Every observation we make is constrained by instruments, noise, and finite data. Even something as seemingly simple as measuring the temperature of the cosmic background radiation in different directions faces subtle challenges. Detectors have noise. Foreground emissions from our own galaxy interfere. We must subtract various contributions and apply models to extract a signal. At each step, we introduce assumptions. When we search for tiny signatures that might distinguish one cosmological model from another, those assumptions matter. In scenarios like conformal cyclic cosmology, the predicted imprints in the background radiation are extremely subtle. We are looking for faint patterns on top of noise. Different statistical methods can lead to different conclusions. Detection versus non-detection is often not a sharp line, but a matter of confidence levels. Even more fundamentally, our universe is just one realization of whatever underlying process generated it. We cannot rerun cosmic history with different parameters and see how the outcomes compare. We have a single sky, a single large-scale structure. This makes some probabilistic questions especially hard. We can ask, how typical is our universe among all possible universes? But we only observe one sample. Any answer must use assumptions about that hypothetical ensemble. This is known as the measure problem in cosmology. When dealing with infinities, how you define probabilities over an infinite set can change the answers. Different choices of measure, different ways of cutting and comparing an unbounded structure can yield different assessments of what is likely. There is no universally agreed principle that selects a single measure for the multiverse. So even when models predict infinitely many regions, we still confront ambiguity when we ask what fraction of those regions have certain properties. The more subtle the question, the more sensitive the answer becomes to these choices. Layered on top of measurement limits and model ambiguities is observer bias. We do not observe the universe from a neutral standpoint. We observe it from a specific location as specific kinds of beings. We are made of baryonic matter, not dark matter. We live around a mid-mass star in a quiet galaxy in a relatively unremarkable cluster. We exist at a cosmic time when stars still shine and structure still forms. Our very presence filters the kinds of situations we can observe. We cannot find ourselves in a universe that does not allow for observers like us. This selection effect is the basis of anthropic reasoning, but it is also a source of bias. When we see that the constants of nature seem finely tuned for complexity, we may be tempted to infer purpose or necessity. Yet at least part of that fine-tuning may be an observational filter. If there are many regions with different parameters, we necessarily inhabit one of the rare regions where we can arise. This is not a complete explanation of fine-tuning, but it warns us against overreading meaning into the fact that the universe is hospitable to us. It also complicates probability arguments. When we ask, how probable is it to find conditions like ours, we must specify relative to what ensemble of possible conditions and under what notion of typical observer. Different choices can lead to different answers. Beyond these structured biases, there are unknown unknowns, features of reality that our current theories do not even hint at. History of science is full of them. Before the discovery of galaxies, the universe was thought to be the Milky Way alone. Before the understanding of quantum mechanics, the behavior of atoms was mysterious. Before dark matter and dark energy were inferred, we believed most of the universe's content was ordinary matter and radiation. Each step revealed layers we had not suspected. It is likely that our current picture is still incomplete in ways we have not yet imagined. There may be aspects of space-time, of quantum fields of information, and of consciousness that future theories describe very differently. Those new descriptions may change how we think about infinite ensembles, about cycles, about recurrence. When we speculate now about eternal return, we do so inside the frame of present-day physics. Future insights may widen that frame or alter it. This is not discouraging. It is a reminder of scale. Our best theories are powerful tools, but they are tools built by a finite species on a small planet. We use them to reach far beyond our immediate surroundings. But we must remember that the map is not the territory. This brings us to a final distinction. The difference between poetic speculation and physical science. Both have a place in thinking about eternal return. Poetic speculation takes ideas like infinite universes and cyclic time and explores their emotional and existential consequences. It asks, how does it feel to imagine that every choice might be made in some branch? What does it mean for meaning if my life is one of many repeats? It uses metaphor, imagery, and narrative to bring abstract possibilities into contact with lived experience. Physical science plays a different role. It constructs models with precise equations. It makes clear assumptions about what exists and how it behaves. It uses those models to generate predictions that can be compared with observations. It quantifies uncertainty, tests alternatives, and refines or discards what does not match data. When we talk about eternal inflation, Poincare recurrence, or cyclic cosmologies, we are in the realm of physical science. We examine whether given assumptions lead to certain mathematical consequences. We check whether those assumptions are consistent with what we see in the sky. When we talk about the eerie feeling of living a life that might repeat, or the strangeness of sharing a pattern with distant copies, we are blending science and poetry. Both modes are valid, but it helps to keep track of which mode we are using. When speculation walks too far from what models support, it risks becoming untethered. That is not always wrong. Imagination often runs ahead of proof. But if we wish to remain honest, we must label clearly which claims are supported by theory and data, and which belong to the open space of possibility. As you lie here thinking about eternal return, you are doing both. Part of your mind is holding on to the scientific threads, probability, entropy, multiverses, recurrence theorems. Another part is feeling what these ideas mean for a single life, for this life. In the end, one simple perspective can bring calm. We are tiny observers on a small world in a vast cosmos. Our theories reach far, but not infinitely far. Our intuitions guide us in daily life, but falter in the face of infinity. Our measurements are delicate and partial. Our point of view is filtered by the conditions that allow us to exist. Yet within these limits, we can still glimpse profound structures. We can see that reality may be much larger than the region we inhabit, that time may have depths we cannot plumb, that patterns like ours might arise more than once. We cannot say with certainty whether every life repeats, or whether each is a singular event. We cannot yet tell whether the universe cycles forever or expands into some new phase we do not understand. What we can say is that the questions themselves are signs. Signs that in a small corner of a vast reality matter has arranged itself into patterns that can wonder, patterns that can step back from immediate survival and ask, what kind of world is this? What does probability mean when the sample space may be infinite? Where do the limits of understanding lie? In contemplating eternal return and the immense structures that could enable it, we are really contemplating the gap between human scale and cosmic scale. Between finite minds and perhaps infinite worlds, the gap does not close, but in the quiet between thoughts, you can let that be. You do not need to solve infinity, you only need to rest inside it, aware that whatever the ultimate truth of recurrence, multiverses, and cycles, you are for this brief span a point of awareness inside a reality much larger than thought. Tonight you have spent time with very large things, with infinities and multiverses, with cycles of universes breathing in and out, with patterns of identity that might repeat across aeons. It is a lot for a human mind to hold, but you do not need to hold it tightly. You can let it wash over you, like waves of thought slowly rolling in and quietly receding. Beneath all of the theories, beneath the equations and models, one simple image remains. The universe is vast. Your life is small. And somehow this vast universe has produced a small being capable of noticing both facts at once. That is already a quiet miracle. Think for a moment about cycles, not cosmic ones at first, just the cycles you already know. The turning of Earth bringing day and night, the rhythm of breathing, in and out, the beating of the heart, contraction and relaxation, sleep and waking. Even your thoughts move in cycles, attention and drifting, clarity and fog. This alternation is not a flaw. It is part of how living systems stay balanced. No organism is on all the time. Cells repair during quiet phases. Memories consolidate as the brain moves through sleep. The body and mind use cycles to maintain themselves. When cosmology speaks of cycles, of universes expanding and contracting, of aeons following aeons, it is tempting to feel overwhelmed. But you can also let the idea blend with what you already know. Nature often uses repetition, not simple loops but spirals. Events do not come back exactly the same, but themes recur. Stars form live and die. From their remnants, new stars and planets are built. On some of those planets, chemistry explores many possibilities. Life arises and evolves. Patterns of complexity emerge and fade. Perhaps on very large scales, universes themselves have analogous rhythms. The comfort of cycles lies partly here, in knowing that endings may not be absolute, that dissolution at one level can become raw material for formation at another. You can feel this even within one life. Old versions of you dissolve, new ones take shape, interests fade and new interests appear. Relationships change. There is grief in that, but also possibility. If the cosmos is also layered with cycles from microscopic to universal, then impermanence is not a mistake. It is structure. From a scientific standpoint, impermanence is linked to entropy. Configurations that are highly ordered are fragile. They occupy small regions of possibility space. As time passes, systems tend to spread out into more probable disordered states. From a human standpoint, this looks like loss. The clarity of youth blurs. Memories dissipate. structures crumble. Yet the same principles that allow decay also allow diversity. Because matter and energy can flow, because structures do not last forever, there is room for new structures. Stars ending in explosions seed galaxies with heavy elements. Those elements form planets. On at least one planet, they form brains in which questions arise. The beauty of impermanence is that it enables variation. It allows for many different kinds of experiences to exist in the same universe. If everything were eternally fixed, nothing new would ever appear. In a repeating cosmos, this logic extends further. Even if certain broad patterns are recurring, the specific path that consciousness takes through those patterns is always lived locally. You never experience all cycles at once. You experience this moment, this breath, this stretch of awareness. You do not need to solve eternity to appreciate it. Then there is the mystery of consciousness. All of the cosmological models speak about matter and energy fields and geometry. They tell us how structures can form and reform. But they do not yet explain why some of those structures are accompanied by experience. Why a certain arrangement of neurons and signals should be linked to the feeling of being. There are theories. Some focus on information and integration, others on quantum processes or on computational properties. But none has yet produced a complete account that most scientists accept. From one perspective, this is a gap. From another, it is an invitation. It means that when you lie here, feeling the weight of your body on whatever surface supports it, feeling your breath move in and out, you are participating in a phenomenon that physics cannot fully describe. Even if the cosmos turns out to be cyclic, even if patterns like yours arise many times, the fact that there is something it is like to be that pattern remains a deep question. You are not merely a configuration of particles. You are also the awareness of that configuration. Gratitude for awareness can be very simple. It does not require answering big questions. It can be as straightforward as, I am glad that there is experience instead of none. Glad that there is a universe containing atoms and stars and also moments like this one, where a mind can contemplate its own place in that universe and then gently let the contemplation fade into quieter states. Sleep is not the opposite of this gratitude. It is one of the cycles that makes it possible. When you sleep, conscious awareness loosens its grip. The brain continues to process. Memories are sorted and strengthened or weakened. Physiology resets. You do not watch every step. You are simply absent from the record, and yet you trust that you will return. In a sense, every night you rehearse a small letting go. You release control, you allow the self-story to pause. In the morning it resumes. In a much larger sense, cosmological cycles, if they exist, might be analogues of this letting go. Long universes of activity, followed by long fades, followed by new beginnings. You are not responsible for managing those scales. You are responsible only for deciding how gently to meet uncertainty. Peace with uncertainty does not mean resigning yourself to ignorance. Science will continue. New instruments will look deeper into space and time. New theories will refine our understanding. Questions we cannot currently phrase will one day be ordinary research topics. But even an ideal intellect, even a hypothetical being with vast computational resources would still face limits. No finite mind can fully contain an infinite structure. No observer inside the universe can adopt a completely external view. There will always be horizons, edges beyond which knowledge becomes inference and inference becomes speculation. Accepting this is not failure, it is realism. When you accept it, you free mental energy that would otherwise be tangled in trying to control what cannot be controlled. You can let questions remain as open spaces, not as problems that must be solved before you can rest. Reality is vast and wondrous. You inhabit a very small region of it. Yet within that region you have access to the calm recognition that many things will always lie beyond you, and that this is compatible with a meaningful life. As you drift now towards sleep, you might picture the universe one last time, not in full detail, just as a wide dark expanse scattered with galaxies. Each galaxy a swirl of stars, each star with the possibility of worlds. Somewhere on one of those worlds a being lies quietly thinking about cycles and recurrence, wondering whether this moment has happened before or will happen again. The answer does not change the softness of the present, the bed beneath the body, the slow rhythm of breathing, the way thoughts grow lighter and less connected, like distant galaxies slipping beyond the visible horizon. You can let them go. Let the questions about eternal return loosely orbit far away. They do not require immediate resolution. They will still be there tomorrow or in some other cycle. For now, you are allowed to rest. The universe is large enough to continue without you for a few hours. Stars will still burn. Galaxies will still turn. Probabilities will still unfold. Even if your awareness steps back, sleep is safe. In a cosmos that may hold infinitely many patterns or endlessly many cycles, this small, finite act of closing your eyes and letting consciousness recede is both ordinary and deeply aligned with how nature works. Activity and rest, expansion and contraction, awakening and sleep. You are part of those rhythms. You can join them willingly. Let your thoughts fade into background noise. Let your attention turn inward and then grow diffuse. The questions about whether we are living the same life again and again can become soft shapes at the edge of awareness, far enough away that they no longer demand answers, close enough that they still lend a sense of wonder. As you drift, remember only this: you are a brief and luminous moment in a universe that may be endless in structure. And this moment is enough. Rest now.